Hello students, this is the instructions for the remaining slides of the Unit 3 project. Remember, we've already discussed the first 6 slides that occurred in the Unit 3 project workday that we had about a week ago. The only updates are that the loop diameter specifications have been updated, so you do need to choose between 25 to 55 meters, as well as I did include the units for the velocity on hill B right here. So make sure that you also update those on your own. So when you open up the link to this updated PowerPoint, you can either use the entire updated PowerPoint and just transfer your information over, or you can just copy and paste yours into your old presentation. So if you go to slides.google.com, again, this is slides.google.com. If you already, if you already have your copy, again, all you need to do is you can highlight slides 7 through 12. They all say new slide. Right click them and copy them. And then if you come over to your original presentation, you can right click here and then paste. You can also do Control C, Control V, and that'll make sure that those extra slides are all included. So we already went over 6 slides, and now we have 6 more slides to discuss. All right, so now we're going to talk about the speed at the top of the loop. Remember, you should choose a new loop height between 25 and 55 meters. Make sure whatever you put on slide 2 matches here on slide 7. Now remember that hill A is 100% potential energy because the roller coaster was at rest. So you'll see right here that we crossed out the kinetic energy for hill A, our starting hill, because we don't need it. The top of the loop, on the other hand, the loop is much shorter than the hill, and therefore it's going to actually have both potential energy from some height, as well as that remaining energy will have to be kinetic energy, meaning the roller coaster is moving. It has motion as it goes around the loop. So based on this, we know that potential energy of the loop plus kinetic energy of the loop is the other side of our equation. Based on this, we want to know what is the velocity of the roller coaster at the top of the loop. So remember that based on this, we had a class on how we can get over to this equation. So make sure that if you haven't done this yet, that you take a look at the total energy video. That way you understand how we got to this equation. But we do know that g times h of the height at hill A equals g times the height of the loop plus 1/2 times the velocity at the top of the loop squared. Remember that g is our magic number, so this is going to be positive 9.8 here and here. All right, so if we were to go ahead and fill this in, we would have 9.8 and right here 9.8. Right? And then right here, again, put in your height of your hill A, which one more time was all the way up here on this slide. So your starting height, max height, that's what you should be plugging in. That is your HA. We already discussed that on slide 5. So HA goes here, and then the height of your loop, again, that's what you put right here. So again, the height of A was from slide 2, and then your height of the loop, that's what's right here. That's where you're going to plug in right here for HL. And then again, another way to write 1/2 is 0.5. So right here, you can just plug in 0.5. That's an easy way to put it into your calculator. So then what you're going to do is you're going to go ahead and multiply 9.8 times your height of your starting hill, your max height, and that number goes here. Then you're going to go ahead and multiply 9.8 times the height of your loop. Remember, multiplication, it makes things that we can simplify. So times the height of your loop, that goes here. And then again, this 0.5 stays here. Now what we need to do is we need to get rid of whatever's furthest away from our variable on its side of the equal sign. So currently what's furthest away is this term right here, which is being added. So what we need to do is we need to subtract this term from the rest of it. All right, so I'm going to actually make this a different color. All right, so let's go ahead and make this red. All right, so if this term is the red term, what you're going to go ahead and do is you're going to subtract the red term from the right side, and that gets rid of it. And you also need to subtract the red term from the left side, and whatever that equals is what you put right here. Okay, so this pink term minus the red term, that's what this equals right here. Again, this right here equals 0.5. All right, so now we're going to go ahead and divide on both sides because you can see here that 0.5 is being multiplied. So make sure you divide by 0.5 on the right, and that gets rid of it. Whatever you do on one side, you also need to do the other side, so divide by 0.5 on the other side, and that's what gives you this right here. Finally, remember we do need to get rid of this exponent, this squaring, and the way that you get rid of squaring something is you square root it. So if I were to square root this would get rid of the exponent, but whatever I do to one side, I also need to do the other side, so square root the other side. Remember the easiest way to do a square root is to go to google.com, and then let me clear this out. Just go ahead and do square root of whatever your number is. So if your number is 5,000, the square root of 5,000 would be 70.5. So that's how I recommend doing it. Otherwise, you can do it with your calculator. All right, and that will give you your speed at your top loop. So again, subtract this term from both sides, and then go ahead and divide by 0.5 from both sides, and then make sure you square root both sides. And that will leave you with your final answer. If you need help, always make sure to reach out to us. All right, taking a look at slide number 8, this is where we're going to take a look at the centripetal acceleration at the top of the loop. So what we need to do is, again, you chose the height of your loop. You can find that in 2 places. So you can find that on slide 7, all right, from slide 7 or from slide 2. Remember, both of those should have the same answer. Again, I did update slide 2, so make sure you also update slide 2 if you already had the original presentation. So what is the radius of the loop? It's going to be your height of your loop divided by 2. So if your height of your loop is, again, it must be between 25 and 55 meters, right? So for example, if it was 50, you would plug in 50 divided by 2 would give you a radius of 25 meters. So again, make sure that you plug in whatever yours is though. All right, so again, that should make sense because the height is going to be a diameter, which is all the way from bottom to top, but a radius is half of the diameter. And since the diameter is the height, that just means it's half the height. So that's going to give us the radius of our loop. Now, why do we need to know that? Well, remember that we discussed on slide number 6 all about centripetal acceleration, which is velocity squared divided by r. So going down back to slide number 8, we see that equation again. So we see the velocity at our loop squared divided by the radius of our loop. And this is going to be specifically taking a look at the top of the loop. Please note that we should, in real life, calculate the bottom of the loop, but this is not real life. This is just a project, and that would be a much more complex calculation. So we're just going to ignore that one for now. We're only paying attention to the top. Okay, so what is the centripetal acceleration at the top of the loop? It's going to be our velocity squared divided by our radius. So taking a look, remember the velocity of our loop is what we just solved on slide 7. So coming back here, you just solved that right here. So this is literally what we just solved. All right, so again, let me go ahead and I will type that up there for us so that we remember that the velocity of the loop, oh, I already typed it up there. Awesome. So the velocity of the loop, that's what we solved in slide 7. So what you're going to go ahead and do is put in that velocity of the loop from slide 7, and then the radius of your loop, which you just solved right here, right? So that goes in the radius of the loop. Remember that you do need to do the square first, and so whatever you get once you square your velocity, that goes there. And then finally, you can divide by your radius. Remember that this right here is the same as a division sign. And then there will be your acceleration, centripetal acceleration. Now the question is then, will your rider survive the top of your loop and why? So remember, going back to slide number 6, we calculated that the max centripetal acceleration we can have at the top of the loop was 5 Gs, right? We can tolerate up to 6 Gs, but at the top, there's also the G from your own weight that you need to account for. So remember, we already decided, we answered this in our first session, that this should be, sorry, let me highlight this, that this should be 5 Gs, and remember that 5 Gs times 9.8 is going to give us, right, let's go ahead and do that. So 5 times 9.8 is going to give us a max acceleration of 49 meters per second. That won't kill us. All right. So remember, we want whatever our acceleration to be less than 45. All right, so let me go ahead and I will pop that back over here. So again, this was slide 6. Again, this was already discussed in a previous class. So what you should be thinking about here, right, is if your answer is less than 49 meters per second squared, then they will survive, right? Because, and the reason why is because that's less than 5 Gs of force, 5G forces, right? Whereas if it's more than 49 meters per second squared, Well, obviously they're not going to survive because that's more than 5 Gs. So make sure you take a look at your answer here and compare it to this. So compare to this, you want your answer hopefully to be less than 49 meters per second squared so it doesn't kill your riders from too many Gs. Okay, so that is slide number 8. Now for slide number 9, we're going to take a look at what's the velocity at ground level. So at this point, we've calculated velocity at the top of the secondary hill, hill B. We've calculated velocity at the top of the loop. And now we're going to go ahead and calculate the velocity at the actual ground. So remember, this brings us back to our total mechanical energy at every point is the same. So the total mechanical energy from our starting hill A is going to be the total mechanical energy from the ground. So remember, we have done this several times. Hill A is 100% potential energy because it starts at rest. There's no kinetic energy, so you can cross out the kinetic energy part on the left-hand side. Again, this goes back to a previous lesson. Make sure you've watched that lesson and understood it. At ground level, it's a 100% kinetic energy actually, meaning your fastest motion, fastest velocity, right? So this is going to be the fastest that you move on your roller coaster. And the reason it's all kinetic energy is because you no longer have height, so there is no potential energy to consider. So that actually makes this equation pretty easy, right? If when we simplify this, the potential energy, the potential energy at part A, so our initial big hill right here, is going to equal our kinetic energy at the very bottom right here. So this was at A, and this is at G for ground. So potential energy at the top of A is equal to kinetic energy at the ground. Remember, we know that equation, that potential energy equals mass times gravity times height on the one side, and kinetic energy equals 1/2 times velocity squared times mass on the other side. But remember, we can get rid of masses because the mass is the same on both sides. All right, so that being said, let's go ahead and take a look at this. Remember, G is our magic number, that's 9.8. And the height of our roller coaster, that's our max height. Again, that was just from slide number 2. That was the max height that you chose for your overall first hill. Okay, so you'll plug that in, you'll put 9.8 here, and you'll put your height of whatever your roller coaster is here. Remember that another way to say 1/2 is 0.5, so that's what goes there. Now at this point, you can go ahead and simplify the left-hand side. Right, so 9.8 times whatever the height of your initial starting hill, right? So height of this hill right here, that is what is going in here. Now, and again, don't forget, I'll go ahead and take a different color here. This is going to be 0.5. And now I need to get rid of whatever's furthest away from my variable, which is currently multiplying by 0.5. So we're going to divide by 0.5 on the right to get rid of it. But whatever I do to one side, I also need to do to the other side. So divide by 0.5 on the other side. So take this number and divide it by 0.5, and that should be your v squared. Now we still need to get rid of this squared. All right, that's the next thing to get rid of. And remember, to get rid of that, you're going to go ahead and square root it, and that gets rid of the squared. But whatever you would do to one side, you also need to do to the other side. So square root the other side as well. And so again, the easiest way to do that is just Google what is the square root of blah, blah, blah. And then that's going to be your final answer in meters per second. All right, so that will be your final answer right here. All right, let's go ahead and take a look at slide number 10. So slide number 10 has to do with work and power, our most recent topics. So remember that the work done to get to the roller coaster to the top of starting hill A is actually equal to its potential energy at the top of starting hill A. And that should make sense because remember, we defined work as a change in energy. And so to get to the top of your starting hill A, you need that change in potential energy, which would also be the work. And remember, we proved this at the end of one of our classes where work equals force times distance. And because we know that force is the same as mass times gravity and that the distance is actually the height of our hill, then work would be mass times gravity times height, which is the same exact equation that we originally saw all the way on slide 4, mass times gravity times height of hill A for potential energy. So that's the same as our potential energy. So therefore, what is the work done for hill A? You don't have to recalculate it, just grab the answer from slide 4. So again, grab this answer right here. That is going to be the work done to get your roller coaster to the top of its hill. Remember, a motor is going to take your roller coaster to the top of its hill before it allows it to drop, right? So it's going to drag your roller coaster all the way up before it drops and begins the actual ride. Okay, so again, that's just from slide Number 4, easy peasy, don't have to recalculate it. Now that being said, go ahead and choose a motor horsepower that you would like. You can choose between 20 and 200 horsepower. Make sure you actually click here and type out what you want. So get rid of this text and actually type out what your horsepower is between 20 and 200. Then calculate that power in watts. We talked about how horsepower, 1 horsepower is the same as 745.7 watts. So we need to multiply it by that. So take whatever you took, like 100 horsepower, multiply it by 745.7 to get your final amount of watts here. So again, just multiply this number right here. Again, this number came from here. Okay, now how much, it should be a pretty big number, just FYI. So for example, 100 times this number would be 74,570. So it should be a pretty big amount of watts. Now, how much time would it take your roller coaster to get to the top of hill A? So remember that our equation is power equals work divided by time. Anytime we have a variable on the bottom that we want to solve for, we can actually switch places. All right, so there's a bit of algebra involved in that. I'm not going to show it to you right now. Just know that when this is rearranged, time also equals work divided by power. So we can actually take this equation, rearrange it, and figure out how long is it going to take to get our roller coaster to the top of the hill. That awful wait time that we're waiting for the motor to get us to the top. So this is going to be from your work. Again, so grab this number that was your work. Again, this should be a really big number. This should be like if you had 120 meters, if you had the highest height and the heaviest motor, so that would be mass, which is 800, that would be the highest one, times gravity, 9.8, times your height, the highest possible height is 120. So that's a really big number. So your number should be somewhere around this. Your smallest possible one would be 600 times 9.8 times 80. So 470, 400 to 940,800 should be somewhere where your work is. Okay, so that's what gets plugged in for work, and then just go ahead and divide it. Remember dividing here by the power that you just solved for. So again, this is the power that we just solved for. Again, that should be a pretty big wattage, around 74,000, right? 20 times 745. Sorry, where did my calculator just go? Calculator. All right, here we go. So again, the minimum horsepower would be 20 times 745.7, so 14,914. The max would be 149,140. So again, this should be a pretty big number too. And then divide that and you should get that answer in seconds. So your answer will be in seconds. Now seconds is okay, but we would rather have it in minutes because that's what most of us know. Remember there's 60 seconds in a minute, so just take your number that you had and divide it by 60. So divide it by 60 and that will give you the number of minutes. So if you have 60 seconds, divide that by 60, that equals 1 minute. Please note that this doesn't take into account the incline of our roller coaster, but for, again, the sake of simplicity, we're just going to go ahead and stick with this, and we'll talk about incline on a different slide instead. Okay, so the last slide before the reflection is just about mechanical advantage. This one's a really easy one. We know the mechanical advantage equation. So assuming that the slant or hypotenuse, so again, if this is our roller coaster, all right, we're going to assume, right, this is our height right here, and this is going to be the slant or hypotenuse. This will be the length, okay? So assuming that here's our roller coaster. Assuming that the slant or hypotenuse, again, the length right here, of your inclined plane leading up to the top of your hill, all right, so this is our HA, height of our hill A, is 200 meters long. We want to know what is the mechanical advantage. Remember, HA, again, is from slide number 2. That's just the height of your starting hill. That should be a very familiar number by now. Now, the length here of this slant, we are saying right now, is 200 meters long. Remember, it starts with the letter L, so that's our length, right? So you're going to plug in 200 for this. And then HA, again, that's what you got from slide 2. That's what you decided the height of your hill A was. And then you're just going to divide those numbers. 200 divided by this number, make sure you plug it in correctly. 200 comes first. And then that will be your mechanical advantage. Now, we want to do the same thing if our hypotenuse this time was 350 meters long. So same thing, you're going to use your height A, but this time your length is going to be 350 meters. Okay, so we would plug in 350 meters, divided by the height of our hill, again, from slide 2 that we plug in here, and that would be our mechanical advantage for this type of inclined plane. Now, imagine you are the engineer because you are in fact designing the roller coaster. If you had to maintain the roller coaster and fix it, which hill would you prefer to walk up and why? So the hill that we would probably prefer to walk up is the one that's easier, right? The one that is easier, right? So easier. Um, and remember that easier means that it has more mechanical advantage. So we're looking for a number that is a bigger number. So if you think of mechanical advantage equals this number, remember that it's this number times easier. All right, and same thing over here, it's this number times easier. So it's 2 times easier, 3 times easier, 4 times easier. You want to choose the one that has a bigger number. So if this one ends up with a bigger answer, that means it's this many times easier, versus if this one ends up with a bigger number, then this one is that many times easier. So you would say, I would rather walk up the 200-meter long hill or the 350-meter long hill, right? So I would rather walk up the, right, so 200, 350 meter hill because dot dot dot, it would be blank times easier. It would be blank times easier, right? So something like that. Okay, so that would make sense for an answer there. So easy peasy slide. All right, let me go ahead and clear this off and then just talk about the conclusion. So for your reflection, based on your calculations analyses, so you've done several slides of calculations, you've taken a look at how does your initial height affect everything, how fast you go, will your loop kill anybody, talking about how long is it going to take a motor to get it to the top. So do you need a stronger motor, et cetera, et cetera. So based on your calculations and analyses, what is one measurable thing that you would change about your roller coaster design? So again, there's lots of different ideas here, right? So maybe you want to increase height of hill A so it goes faster, right? You could do something like you need to fix the loop so it doesn't kill anyone. Remember, the bigger loops are safer. Bigger loops are generally safer. There isn't a risk of you falling from the top of the loop if it's too big. You might want to take a look at, you don't want to go as fast, so maybe you want a lower hill, so you go slower. Again, you might want to think about you want a better motor, so higher motor power, so that you get to the top of the hill faster, or maybe a lower motor so you can sightsee as you go up. So again, there's lots of different things, right? You can talk about work and power. You can talk about maybe you want a different mechanical advantage. Maybe you would want to increase this hill even more so that you would have an even easier time getting up the hill. Just keep in mind that in real life, that would take a little bit longer, right? So we could also say something about like changing the inclined plane to make it easier or harder to walk up if you're a worker, for example. Let's see here. Anything else that I can think of? Right, so loop height. Maybe changing the size of your second hill to just make it more fun, right? You might want to make your second hill bigger, smaller, et cetera, et cetera. So I can put that up there too, right? Make second hill be bigger or smaller, depending on what you want. All right, so there's a lot of options. Just give me one measurable thing and explain what is that one thing that you would change. So don't give me like colors. Don't be like, I would rather it be blue. I want something that we could eventually measure. So say I would change the height, I would change the speed, I would change blah, blah, blah. Okay. What would you name your roller coaster and why? And do you feel that your drawing represents this? Remember, I said very strongly that we would prefer a hand-drawn picture on slide number 3. If it's hand-drawn, again, make sure that you do write your name written on it before taking a picture so we know that it is your picture. And then remember to insert this. Again, this was all reviewed in a previous video, but to insert this, go to Insert, Image, Upload from your computer. Again, the easiest way to get it onto your computer, if you take it on your phone, is to email it to yourself or upload it to like Dropbox or to Google Cloud, Google Drive, or to any other cloud to get it to a computer. Okay. And if you need help, obviously reach out to us. You can always email it to us, and we can email it back to you. All right. So what would you name your roller coaster and why? So again, tell me what would be the name. Why would you name it? And again, the reason we want you to hand draw it is because we want to know, does your drawing represent this? So does it have specific colors, specific designs? Did you add a bunch more loops that we didn't do calculations for? We only did calculations for one loop, but did you add more things that you feel like would have represented your roller coaster? And finally, would you ride on your roller coaster? Why or why not? This is just getting to know you. Obviously, not all of us want to ride roller coasters. Now, the one last thing that I do need to explain here is that for your drawing, again, I recommended in the previous video, right, use the curve tool. As you click through it, it creates a nice curve. And even if you mess up, and remember that um, you do need a hill A, hill B, a loop. This loop should actually be shorter, so I'm going to right click it and edit it. Remember, you can actually use these to edit the points and clean it up. So again, right click, edit. Again, this is the curve tool. So when you go to the lines, scroll down to the curve tool. All right, but then you can move all of these until it looks nice. But again, I do prefer that you just hand draw it. But the one thing that I do want to mention is that you do need to write your heights on here. So you do need to go ahead and tell me, right? There's a, oops, so here's the text tool. So you're going to go ahead and tell me this is my hill A, which is blank meters, right? And then this, and so we want to be labeling this because otherwise we won't be positive which of your hills is if your hills are right. Hill A should come first. Hill B, how many meters is that? And then write your loop, how many meters is that high? All right, so make sure that you're labeling this. Again, your hill A does have to come first. I'll write that up here. So hill A must come first because that gives you the velocity you need to make it through the entire, the energy you need to make it through the entire process. Hill B and the loop can switch, right? So we could do either order for those as long as they don't come first. And both of these, both should be drawn shorter than hill A. Because remember, if they were taller, you would never make it to the top of them in real life. And you, especially on the loop, you could die, right? So we want to make sure that the hill B and hill loop should actually be drawn shorter than hill A and again, labeled. So please make sure that you label those. All right, so that should be your entire project. Remember, before you submit it, you're going to go ahead and go to File and then Download. And when you go to download it, you can download it as a PowerPoint or a PDF. PowerPoint is preferred, but PDF is fine. And then you'll go ahead and you will turn it into the Unit 3 assignment folder. I'll show you where that will be. You won't be able to see it yet, but let me go ahead and show you what it looks like. It hasn't opened yet. It'll open tomorrow. So when you go to Tools and Assignments, you will see it right here. So again, I'll show you just for now the Unit 2 project. All right, Unit 2, you would go all the way down to add a file. Obviously, go to the Unit 3 one, but you would go down to add a file, My Computer, upload it, and upload your file that you originally downloaded. All right, again, if you need help with that, let us know. But otherwise, you should be all set. Thank you so much, and we will talk to you later.